We've studied static electricity, or electrostatics, for the past couple weeks, where we might have a few charges in space and we think about what's going on with space, or what would happen to this proton because this electron exists. What kind of force would it feel? What would the electric field be there? What kind of voltage would be created at that point? Or what kind of energy does this configuration have? Now we're moving towards electric current, and ultimately to circuit diagrams and thinking about how charges would move within a circuit. Now, the electric current will be defined as the rate of flow of electric charges. The rate of flow of electric charges. So if I have some wire here and some electron there, more specifically the current would be the amount of Q, or of charge that flows past a location in a material per any given time. That flows past a location in a material per time. So what might the rate of flow depend on then? Well, the rate of flow depends on what kind of material we're talking about, right? It's easy to get electrons moving through copper compared to rubber. So the type of material, and also, well, maybe the electric potential between the material. So maybe this would be 50 volts of potential difference, and we would get some flow of electric charges. But if I up this to 100 volts rather, then the electrons would move much more rapidly through this material. So it must depend also on the electric potential, or voltage, across the material. Now, conventionally speaking, we typically look at positive charge because of this guy named Benjamin Franklin. Oh, that one's dead. Conventionally speaking, electric current is typically defined as positive charges moving. So even though I'm looking at electrons that are moving through this wire, and it's the electrons that are flowing in any given metal, we define our diagrams as though it's the positive charges that are moving. As movement from positive charges. So the analogy that I'll make is one of water flow. So if you have turned on your sink, you obviously get some water that flows out. But if you've ever turned on my sink in the front, or one in the chem lab, you notice that it will jet out water at a much more rapid pace. So we could say that at your home, there's a smaller pressure within the water pipes, so there's less flow. Whereas here, there is greater pressure and greater water flow. The pressure itself relates to the electric potential. So if there's a higher electric potential difference, then there's a greater pressure of electrons, in the case of electricity, to move through a material. And we could express this algebraically like this. The current is the change in charge over time, or the movement of charge over time. So this is current. We measure it in amps. So 1 amp is equal to 1 coulomb second, or coulomb per second, I'm sorry. And instead of writing out amp, you could just say 1A is 1 coulomb per second. So let's get back to this convention. I just want to show you what this would mean if I have some wire here, and let's say that I've built up some positive charge over here and some negative charge over there, so that there's a potential difference and there's an electric field. Then if I have this, if I have a proton here, I know that it's going to feel a force that way, and if I have an electron, it's going to feel a force that way. Conventionally speaking, the current will be drawn to go in that direction. But we know that it's really the electrons that are flowing that are directed that way. But we will draw our arrows on our diagram to represent positive charges moving that direction. Okay. That's our introduction to current. Next, we will be moving to circuits.